Log on, tune in, find out. Another good idea from Cambridge.
Second part of the morning section with Dr. Azhar Hussain of Veer Kunwar University, who will talk about some theorem of Eulerian integrals of multivariable hypergeometric functions and their application.
First of all, thanks to organizer to give me a chance here for the presentation of my paper. This paper is collaborated with Professor H.M. Srivastava, Institute of Victoria, Canada. And my topic, some theorem on Eulerian integrals, multivariable H function and their applications. Now, first of all, to give introduction and preliminaries. Sorry. Now we know that Eulerian integrals and Eulerian beta integrals b alpha beta is equal to 0 to 1 t alpha minus 1 1 minus t alpha minus 1 dt is equal to gamma alpha gamma beta gamma alpha plus beta. Here real alpha and real beta greater than 0, and equation 1 can be changed in the second equation a to be t minus a alpha minus 1 beta b minus t beta minus 1 dt is equal to b minus a alpha minus beta alpha plus beta minus 1 b alpha beta. Real alpha real beta greater than 0, here a not equal to b. Now since this is a ut plus v binomial expansion, and this can be written as au plus v gamma is equal to L is equal to 0 to infinity minus gamma L factorial t minus au plus v L. Here conditions are mod t minus a u less than mod au plus v mod, here t belongs to ab, close interval ab, closed and open, where lambda n is equal to, we know that gamma lambda plus n by gamma lambda. Now this is the second equation we can change, a to be t minus a alpha minus 1 b minus t beta minus 1 ut plus v gamma dt is equal to b minus a alpha minus beta minus 1 au plus v gamma b alpha beta into 2f1 alpha minus gamma alpha plus beta minus b minus au plus b. Here real alpha greater than 0 and real beta greater than 0, and mod argument bu plus b divided by au plus b less than equal to pi minus epsilon. Here 0 less than epsilon less than pi and b not equal to a. Now we know that the
so this is the Euler integral
yes.
So
now here
transformed arguments.
yes. Here we know that PFP denotes the generalized hypergeometric function. P is the numerator and Q is the denominator. And the argument conditions emerges from the analytic continuation of the Gaussian hypergeometric function. Now here 2f1 occurring on the right hand side of this above equation, we are setting for gamma is equal to minus alpha minus beta, and second member of 1.4 simplify the considerably, and we further set u is equal to lambda minus u and b is equal to 1 plus mu b minus 1 plus lambda a. Now these are results from above writer. I can show you by the 1981 maybe. A to be t minus a alpha minus 1 b minus t beta minus 1 b minus a lambda t minus a plus mu b minus t lambda plus mu dt is equal to 1 plus lambda minus alpha 1 plus mu minus beta by b minus a b into alpha beta. Here this making use of above equation, Rana and Srivastava 1994 addressed the problem of closed term evaluation of the following general Eulerian integral. And this is just Ix is equal to A to B, and this is 1.6 equation, and condition where f of t is equal to b minus a rho t minus a plus sigma eta minus t, g of t is equal to t minus a gamma b minus t lambda f of t 1 minus lambda gamma minus lambda divided by b minus a beta b rho plus alpha minus beta t minus a beta sigma b minus t. Here we know that the h function 1926 by the Fox defined by this equation H7 PQ Z AI AJ VJ BJ 1P Q1Q is equal to 2 pi I zeta theta zeta Z zeta T zeta. Here I is equal to root minus 1 C 0 in singleton Z zeta is equal to exponential zeta log mod Z plus I argument of x, where log mod Z represents the natural logarithm of Z of mod Z, and argument is not necessary to principal value, principal part. Here for convenience theta zeta equal to this, and empty product is interpreted as above, and these conditions are where the integers m and pq satisfy the inequalities. 0 less than equal to n less than equal to p, and 1 less equal to m less than equal to q. The coefficients aj greater than 0, j is equal to 1 to p, and bj greater than 0, j is equal to 1 to q. And the complex parameter aj j is equal to 1 to p, and bj j is equal to 1 to q. Here and so constrained that no poles of the integral integrated in above equation 1.9 coincide, and lambda is a suitable contouring of the Marian bars type in the complex zeta plane, which separates the poles of one product from those of the other. Further, if we let sigma gamma is equal to this, the integral is above equation 1.9 converges absolutely and defines the h function analytic in the sector. Mod argument z less than 1 by 2 gamma pi, the point z is equal to 0 being actually excluded. In fact, according to Vatsana 1984, the h function makes sense and defines analytic function of z also. Then either gamma is equal to j is equal to 1 to p minus j is equal to 1 to p, bj is less than 0, and 0 less than mod z less than infinity, or gamma is equal to 0 and 0 less than this condition. Recently, Saxena and Soto 1982 made use of the integral formula in order to evaluate the following Eulerian integrals in the form of this. They also considered a number of interesting special cases of the integral formula in the above equation 1.15. In each case, however, the results were expressed in terms of h function of two variables. The present paper has been stemmed essentially from our attempt to express the integrals above equation 1.15, and indeed all those are contained in 1.15 in terms of a special function of several or of similar or lesser complexity. Thus, in general, we derive expressing an Eulerian integral of the type 1.15 in the form of formula theorem involving the h function of R variables in terms of h function of R variable. Now, here another we have used different integral operator by setting b is equal to x. By setting b is equal to x of the Eulerian integrals, Rana and Srivastav 1984, and Saxena and Nipsto can easily be rewritten as a fractional integral formula involving the fractional differ integral operator a d nu x as defined by this, provided the integral exists. D x nu is equal to 0, d x nu belongs to complex C, correspond to the classical Riemann-Lebedev integral fractional derivative or integral of order nu or minus nu. Moreover, when alpha tends to infinity, the equation 1.16 above equation may be identified with the definition of the familiar Weyl fractional derivative or integral of order nu or minus nu. We can see of the LDI result. Now, these are the competition and these are the work in the field of the fractional integration. Now, following various conventions and notation, we have used the following writers, S.M. Srivastava and et al. These are the 2124 S.M. Srivastava and his worker. And these Z1 to Zr is equal to H0 n M2 N1 Mr Nr. This is the equation of 1.18. Now, here denote the H function of R complex variables Z1 to Zr. Here the convenience Aj alpha dash j alpha j r. Aggregates of P member array A1 alpha dash alpha 1 dash alpha 1 r to AP alpha dash P alpha P r, while Cjk Yjk 1 Pk abbreviate the array of Pk pairs of parameters Cjk gamma jk to Cgk gamma k is equal to 1 to r, and so on. Suppose as usual that the parameters Aj and Bj 1.21 equation, and complex numbers and the associate coefficient alpha jk j is equal to 1 to p, j is equal to 1 to pk, beta jk j is equal to 1 to q, delta jk j is equal to qk for every k belongs to 1 to r, and positive real numbers such that gamma k is equal to j to k j to 1 p on equation 1.3 and sigma k is a 1.24. These are the positive real numbers where the integers n p q m k n k p k and q k are constant by the inequalities 0 less than equal to n less than equal to p and q greater than equal to 0, 1 less than equal to m k less than equal to q k and 0 less than equal to n k less than equal to p k, and the equality above equation 1.23 holds true for suitably restricted values of the complex variables Z1 to Zr. Now, where the integers n, p, q, m, then it is shown that multiple bands contour integral in the H.M. Srivastava monograph H.M. Srivastava and K.C. Gupta in 1982, representing the multivariable H function of a introduction equation 1.3 converges absolutely under the conditions above equation 1.24 mod argument zk less than equal to 1 by 2 zeta k pi, where k is equal to 1 to r. The points zk is equal to 0, k is equal to 1 to r, and various exceptional parameters values being tactily excluded. Furthermore, we have h z1 to zr. These conditions are maximum. This and n is equal to 0 minimum mod z1 to zr tend to infinity, where with k is equal to 1 to r, zeta equal to minimum real d jk by delta jk, n k is equal to maximum real r c jk by gamma jk z equal to 1, provided that each of the inequalities one above equation 1.23 to 1.25 holds true. We remark in passing that throughout the present work we shall assume that the convergence and existence conditions corresponding appropriately to the ones detail above the satisfied by each various S function involved in our layers. This is my theorem integral formula. We first state one of the main integral formulas associated with the S function. Behind the all introduction part, and then we will derive the first integral formula, provided in addition to the appropriate conditions and conditions. This existence and A to be t minus a alpha minus 1, b minus t beta minus 1, ut plus b gamma h z1 ut plus b p rho 1 to zr ut plus b rho r dt is equal to b minus a alpha plus beta minus 1 au plus b gamma b alpha beta L is equal to 0 to infinity a l l factorial l plus beta 1 minus b minus au plus b z1 to this one 0 to n1, and this is the, and conditions are minimum rho 1 to rho r greater than 0, b minus u by au plus b less than 1, here b not equal to 0, and minimum real alpha and real beta greater than 0. Furthermore, we imply the notation h star z1 to zr h z1 to zr n is equal to 0. We obtain the following companion formula 2.1. This is the next formula, provided the condition are exist. Now, we prove the very simple, only setting and direct integral formula of 2.1. We first replace the multivariable S function occurring on the left hand side by Eulerian Burns contour integral by the Srivastava monograph in 1982, and collect the powers of ut plus v and apply the binomial expansion of 1.3 minus introduction, and we get replaced by gamma minus k is equal to 1 to r rho k theta, where psi 1 to psi r denote the variables of aforementioned formula Barium burst contour integral. We then make use of the integral formula 1.2 and interpret resulting Barium burst contour integral and h function of the r variables z1 to zr, where this lead by the final integral of the 2.1. The sufficient condition of validity of above equation, we would follow the applying the principle of analytic continuation. And the second 2.3 formula, we are similarly we can derive by replacing gamma by this and the set zeta is equal to zeta k is equal to r, and these conditions are, and the formulas 2.1, 2.3 can be put in the much more general setting. As a matter of fact, if we imply the binomial expansion 1.3, and this is the yt plus z delta is equal to this equation 4. Simultaneously, we shall similarly obtain the following symmetrical generalization of the integral formula of 2.1 and 2.3. This is the next theorem by 2.5. This is the a to b t minus a alpha minus 1, beta minus t beta minus 1, ut plus b gamma yt plus delta. This is the, provided these conditions are minimum 1 less equal to k less than equal to r, rho k sigma k greater than 0, and maximum b minus a mod b minus a u by a u plus b minus a y b u plus z less than equal to 1, b not equal to a. This is the next companion formula 2.6, and provided the conditions minimum, these are conditions are here, and for several applications of the theorem we are derived by making use of the these conditions, and we get the 3.1 gamma alpha gamma beta gamma is equal to 2f1 बराबर this है 2 pi I is minus I infinity to infinity gamma alpha plus zeta gamma beta plus zeta gamma plus zeta gamma minus zeta minus z to power z minus zeta d zeta, and conditions are I is equal to root minus 1 and argument minus z mod less than equal to pi minus epsilon, 0 less than epsilon less than pi, and pi, gamma not equal to 0 minus 1 minus 2. where the path of integration is indented if necessary in order to separate poles zeta is equal to 0, 1, 2 from poles are zeta is equal to minus alpha minus h and zeta is equal to minus beta minus a s belongs to natural number. This is we can easily abbreviate the integral Eulerian integral 2.1 2.3 in terms of h function of r variables, r plus 1 variables. This is a z r plus 1. Thus, in the special case when r is equal to 1, the integral formula of my 2.1 2.3 can be shown correspond to the main results section on Navito 1992 in terms of L function f3 defined by this, and we get the result here, and where the convergence here. Furthermore, since these are the use the L function, we can derive the integral formula of 3.3 can be written as here, and the last integral formula 3.6 can be proven directly by appealing to the 1.2 1.3 and the obvious companion of the expansion of 1.3. We get the more interesting result of my paper. These are the results of the applications of the special function of the Eulerian integrals, and second member of the these are conditions are z r plus 1 is equal to b minus a u plus b, and z r plus 2 is equal to this, and or z r plus 1 b minus a u by a u plus b and z r plus 2 of this. Here each of our integral 2.1 and 2.3 and indeed also 2.5 and 2.6 possesses manifold generality, first of all by specializing the various numerous variations obtained by letting by desired number of exponents rho 1 to rho r and sigma 1 to sigma r decrease to 0 in such a manner that each of the resulting equation can be suitably applied for the derive the corresponding results involving the wide variety of potentiality useful functions or products of several such functions which are expressible in terms of EFG and h function of one or more variables. For example, n is equal to p is equal to q is equal to 0. The multiple h function occurring on the left hand side of our formulas 2.1, 2.5, also 2.3 and 2.6. And when p is equal to 0, k is equal to 0, we can reduce the rather immediately are different function of h function, a Fox function defined by in 1926. Thus, the table listing various space cases of h function can be implied with the view of the deriving Eulerian integral formulas involving any of these simple S functions desired. Next, we turn to applications, our main results, and these are the results by application of the Eulerian integral formulas, fractional calculus in R variables, and these are the 3.11 the main results. After simplify we get the results 3.11, and which is indeed in this equation 3.10 indeed equivalent to the condition of validity of that integral formula 3.9 to 3.11 are obtained by fairly easily from those of their parents formula 2.1 and 2.5, and thus in each case we require minimum real alpha, real beta greater than 0 and b not equal to a, and that all the multiple hypergeometric functions involved are absolutely convergent. The special cases are for the Eulerian integrals of my theorem 2.3 and 2.3 and 2.6 with the Srivastava and Dodd 1984 generalized Loss-Rela function in their integral are also derived integral function, or these are my special case of this. We also use difference integral formula. With the help of this, we can derive the 3.1, 3.12 and 3.13, and these are the conditions multiple h function, and these are the of my results by the difference numerator integral or differential, and We have the references here. This is for the fractional integral formula 3.12 and 3.313, where the right hand side expect this function of r plus 1 variables, and the addition variable being this one would obviously generalize the main results of the Srivastava and Gupta. As a matter of fact, in each our main results of 69 1982, the factor gamma alpha appears in left side of the. Then further, the involving fractional calculus of Hessel function is more and more variables in the Srivastava work, and these are references. Thanks.
Questions?
I am not so familiar with those H functions of Fox, but do they also satisfy differential equations?
Yes.
Like the Gauss hypergeometric function,
Yes,
which
yes.
is a very special case of the H function, but satisfies a second order differential equation. Is that in general true for H functions, that they satisfy differential equations?
Yes.
Yes?
Yes. By the difference integral formula. Lastly, we have defined it, right?
Oh, you had it. Oh, I missed it.
You mean ordinary differentials?
Yeah, or partial differential equations.
We are using this formula. We get the
Yeah, but
result.
this is with fractional
Yes.
things. But just mean something with ordinary derivatives, of ordinary partial derivatives. So generalizing the familiar differential equations for Gauss hypergeometric functions or
Alright.
Paul hypergeometric functions.
I will not use it.
You don't.
I will try to. Yes. Thank you.
Further questions? Not, let's thank the speaker.